Give them a minute to close the doors. So good morning. I'll just give the last few people that are coming in a chance to enter the room. Okay, so welcome everybody. Welcome back to the conference. Welcome to this morning's plenary. This morning we're going to talk about communities, about why they're so crucial, what we can do to enable them and to sustain them and make them work. And we're going to have two excellent speakers who will approach this subject, I think, from rather different backgrounds and different angles, and give us different perspectives on what communities are and how to facilitate them. They've been spent many years doing that, supporting and facilitating communities in different environments. Our first speaker is Ian Bird. He's the LHC Computing Project Lead. He's also a manager at CERN, and he was before that the operations lead for the EGE project. So he has extensive experience with supporting a very well-known to us community, a very demanding community. And he will talk to us about the fact that we have now had the LHC and the LHC computing infrastructure running for a year, and relate to some of the experiences with that, what we've learned, and how the community is continuing to evolve. So, please, Ian.
Thank you. So, good morning. Is this on? Can you hear me? Yeah. Okay, so I actually won't talk very much about the community. I'll tell you a little bit about what's happened over the last year, our first experience with data. Of course, this will imply a community, but unless you ask me specific questions, I won't go into a great deal of detail on that. So, as you know, the LHC started just over a year ago and has been running very successfully since. And we have learned quite some number of lessons with our first experience with that data, and I'll talk about some of those things now. Okay, so what LHC is doing is looking back in time, essentially, through the evolution of the universe. And we look very close to the start of the universe, very close to the Big Bang, something like 10 to the minus 10 seconds after the Big Bang. That translates into space measurements as very close, something like 10 to the minus 16 centimeters. If you look at the size of the universe, it's about 10 to the 28. And you can think of LHC as a sort of super microscope that allows you to investigate things at the scale which happened very close to the Big Bang. And so actually what we're doing increases the interaction between traditional particle physics, astrophysics, and cosmology. And as you can see, on the scale that we're talking about, matter is really composed of things called quarks. So these are the constituents of the protons and neutrons. So if you haven't seen the news in the last 2 years, you probably don't know what the LHC is. So it's a large accelerator. It's underground, crosses the border between Switzerland and France, 27 kilometers in circumference. There are 4 large experiments situated around this ring. Atlas and CMS are the largest general purpose detectors, nominally to look for the Higgs, but actually general purpose detectors specifically built to look at the physics, a wide variety of physics in this energy range. LHCb is a much smaller detector and is designed to look at the asymmetry between matter and antimatter. One of the puzzling questions that we have is where did all the antimatter go, since the universe probably was created with equal amounts of both. So it looks as though at some very tiny scales, antimatter and matter are not quite symmetric, and that may explain why all the antimatter has disappeared, apparently. So this is something that LHCb will look into. And ALICE is designed specifically to look at heavy ion collisions. And heavy ion collisions give you an idea of the soup of quarks and gluons that existed just after the Big Bang. So we thought it behaved like a plasma. In fact, it certainly looks, with the first results from last year, as though this thing behaves actually like a perfect liquid, which was something of a surprise. Okay, so just to give you an idea of what the computing problem is, if you look at how the accelerator works and what happens, protons are collided in counter-rotating beams in bunches. So at full design goal of the accelerator, there should be something like 2,800 bunches in a beam, and each bunch of protons contains something like 10 to the 11 protons. The nominal beam energy is 7 TeV, which results in a luminosity, which is this expressed in this number here, as something like 10 to the 34 per square centimeter per second. So this is collisions per square centimeter per second. So we have a crossing rate of 40 megahertz, so this is bunches crossing, and which results in a collision rate between protons of something like 10 to the 7 or to 10 to the 9 hertz. Now, that's a very large number, but what's interesting is the rate at which you expect to see new physics, so physics other than you already understand, and this is something like 10 to the minus 5 hertz. So we're looking for very rare events of the order of 1 in 10 to the 13. So this is why we have to take a lot of statistics, and this is why the data and the computing is such a large problem. So just to summarize that, the signal to noise that we have to understand is 10 to the minus 13. The data volume has something we've been saying for actually many years, that the problem will be 15 petabytes a year of new data. And in fact, last year we did in fact record 15 petabytes of data, which was somewhat surprising since this was the first year of running. In terms of compute power, we have always said for a long time 200,000 CPUs. So we have about that in the system at the moment. And 45 petabytes of disk storage, which is what was anticipated for the first year. And I'll come to some comparisons with that in a second. But the real challenge was the funding. The real challenge, not that the funding was not there, because it was. The funding is essentially local. 200,000 CPUs doesn't sound like much. You can have that in a reasonably large computer center these days. The problem is that we don't have such a computer center, and we don't have the willingness of the funding agencies to put all that money into a single computing center. So CERN could provide something like 20% of the total, and the rest had to be found remotely. So whether we liked it or not, the problem was a distributed computing problem. And actually, we have a lot of resources offered to us to do this, but for many reasons, it's better to keep them in the institutes of which they're provided, and use grid technology to bring them together. So that's what we did, and that's what we've been working on achieving for the last several years. So we formed a collaboration, the WLCG, the Worldwide LHC Computing Grid. So it runs and operates a distributed computing infrastructure which provides the framework for doing the data production, the analysis for the LHC experiments. And the collaboration itself is between the experiments and the computer centers. And the collaboration is the important thing here. And one of the important things is that the grid enables this collaboration to work together as a single unit. And as I said, the resources are distributed for essentially funding and sociological reasons. There's a big value to be had in people at universities and labs being able to use the machines and do things themselves. So there's a huge educational value in this. And our task was to make these resources available to the experiments, no matter where the resources were located. So the LHC computing grid essentially is a tiered structure, and I'll talk about this in a little bit more detail. But the system we have at the moment consists of the tier 0, which is at CERN. This is responsible for data recording, but also long-term data management and archiving. So one of the challenges that we have is to keep this data available for 20 years or more, at least the lifetime of the accelerator. And also data distribution, so the data is pushed out from CERN to the tier 1s. And the tier 1s in turn, there are 11 of these distributed around the world, also fairly large computer centers, and they have a similar role in permanent storage. So we have 2 copies of the data, one at CERN and one distributed between the Tier 1 centers. So they also have this role of long-term archiving of the data. They also do a significant level of first-level processing of the data and producing what's then usable for analysis. And that data is then pushed out to the Tier 2s, and there are about 130 of these, where the physicists first get hold of the data and do the real physics analysis. The other role of the Tier 2s is simulation. So we have an enormous simulation load, close in quantity to the raw data, and this comes back up to the Tier 2s. The results of this simulation come back up to the Tier 1, and are archived there. So in terms of where we are, we truly are a worldwide collaboration. We have resources in nearly every continent now. Just recently, we have a site in South Africa. The collaboration itself is the Tier 0, the 11 Tier 1s, and 68 Tier 2 federations. So this more or less corresponds to the funding agencies, or some management unit within the country, and represents something like 130 sites, as I said. And there were 49 funding agencies which signed up to this. So just gathering 49 signatures from funding agencies actually took quite some effort, as you can imagine. So this represents something like 30, in fact today I think it's 35 countries. And in the infrastructure we have this 140 sites, we have around 250 cores, but what's really surprising is that we have something like 150 petabytes of disk. So this, coupled with the networking, which is what I'll talk about later, really opens the way for us to do something which is rather different from what we had planned on doing when we designed the computing model 10 years ago. So then let's just spend a few minutes on the performance of the machine and the experiment. So this gives you an idea of what's been delivered in 2010 and early 2011. I think the LHC itself has worked far better than anybody anticipated, and certainly for a brand new machine, if you compare it with similar experiences with other new accelerators, I think the performance has been really astounding. What you see in the top 2 plots is essentially the amount of collisions delivered in 2010 and the first 3 weeks of 2011. You see in 2011 already it's delivered something like 5 times more than the total of the whole of 2010. And already this is something like a quarter of the stated target for 2010 and 11. And that target, by the way, should be enough to understand whether the Higgs exists or not. The machine itself has already beaten world records for beam energy, beam intensity, and in fact stored energy. And if you look at the little plot on the right, you see here is the goal for last year and what was actually achieved. So this is something like 28 megajoules. At full nominal intensity, this will be something like 130 megajoules, which corresponds to 80 kilograms of high explosive. So you can imagine that this is one of the reasons why the machine people go very carefully in increasing the energy, because making a mistake with this could be very costly. In terms of what's actually been achieved in the machine itself, I said at nominal intensity 2,800 bunches. At the end of these first few weeks here, we achieved 944 bunches, so there's still quite some scope here to increase. The bunches are 10 to the 11 protons. The energy, as you probably know, is only half of what of the nominal energy, and this is why we will go into a shutdown in 2012 to fix some of the problems that prevent us going higher at the moment. The luminosity actually is rather high. Considering this is early days for a new machine, and is approaching very rapidly the design luminosity, and I think this is one of the surprising things, that this has been achieved so quickly. So the signs are very good for the future. Just some numbers from the Tier 0. So in 2010, as I said, we wrote 15 petabytes to tape. On average, we write about 2 petabytes a month, but when the accelerator is colliding heavy ions, this goes up significantly, as you see in the peaks here. So this is the month of heavy ion running, and that's broken down into days. So we again broke some records for the amount of data written to tape per day. We reached over 220 terabytes a day, which I'm told is a world record, but I don't know how to prove that. And that's not something you do on your average backup system, I don't think. So some of the other numbers, so this is a plot which shows the data moving through the tier 0 system, through the storage system in 2010. And what's surprising is that this is an average over the year, which is 2.6 gigabytes a second in, and serving 7 gigabytes a second with much higher peaks. So on average, we're moving something like a petabyte of data a day within the data center, and clearly not pushing all of that out. The grid itself, the performance keeps increasing. We're currently running at something like 1 million jobs a day, rather more than that, in fact. So this is probably, well, it depends how you count. I've got two different numbers here. I have 150,000 here, and I have 100,000 here. There's a normalization factor in here, which you can interpret in various different ways. But, I mean, essentially, the 1 million jobs a day is what we anticipated needing in a nominal year of LHC running, and 2010 was far from being a nominal year. It was a very early year. In terms of CPU time, this continues to increase. In the inset, you see the increase over the last, so this is 2008, and this is the beginning of last year. And in fact, this was already a significant peak, but actually this use has doubled since May of last year. So in January of this year, it was double what it was last May. And actually, one of the things that we started to see was all of the job slots in the tier 1s and tier 2s starting to be filled. One of the other successes is that there are a very large number of users using the system. So that I think even at the beginning of last year, before the accelerator started, there was a certain level of skepticism that the system would actually be usable. But in fact, it has been, and very surprisingly large numbers of people are using the system regularly and successfully doing physics analysis on it. So a sort of take-home number here is that in 2010, the WLCG system delivered something like 100 CPU millennia. So just to prove that it really does work, this is the distribution of CPU time across the grid. So in the top plot, you see the tier 1s and CERN. So CERN is this piece, and then these are the tier 1s. But what's interesting is that the tier 2s are delivering far in excess of the 40% which they nominally were designed to deliver. They're delivering something like 60%, which means that people really are doing a lot of analysis. And that is broken down here, and you see there are some large countries which deliver a lot. But the interesting thing is there are very many small contributions which are used and are effective. And this really enables people in those countries to do things and to have the data themselves and to really work on it. And I think this is one of the important things that we have in this collaboration and that the grid enables, is that people can get the data and can work on it and can be part of the overall effort, even though compared to some other contributions, their contribution is relatively small. So data transfers, so this is one of our concerns when we started this thing, that we would not be able to deliver data as rapidly as we needed to. If you look on the bottom plot, this is basically a summary over from April last year to present day, showing various things that happened during that. Essentially what you should look at here is the level that you see. The nominal data rate that we anticipated was about 1.3 gigabytes per second, which is enough to ship out all of the raw data and the process data and allow capacity for catch-up if some of the tier 1s go down. What you see is that actually we had peaks which were significantly higher than this. We got up to about 5 gigabytes a second out of CERN to the tier 1s. And this was something of a surprise to many of us. And so the fact that we were able to cope with this without really any problem was quite satisfying. The other thing that you notice here is that the 2011 data transfers seem somewhat less than they were in 2010. And I think this is a reflection of the fact that we learnt some of the problems in 2010, and we start to do things maybe a little bit more intelligently than the brute force method. And I'll come to that in a second. So there were some surprises. And in May last year, we found that we were almost filling the whole of the OPN. We were shipping something like, at peaks of something like 70 gigabits a second out of 110 nominal. We didn't really understand why that was. It turned out it was real traffic, and it was generated by one of the experiments starting a processing campaign and pushing huge amounts of data and copies of that data and simulated data all at the same time. That worked, and there was no problem here. It worked perfectly. It was just a little surprise that we saw so much traffic. And of course, this relies on the whole backbone of networking which has been put in place. So of course, the core of this is the LHC OPN, which is the connections between CERN, the tier 0, and all of the tier 1s. So we started with dedicated 10 gigabit connections between CERN and each of the tier 1s, and this rapidly grew to either duplicates or backup routes. Today there are at least 2 routes between any tier 1 and CERN, and this is needed, but it makes it extremely reliable. And of course, we rely also upon the network infrastructure, so Géant in Europe, US LHC net in the US, and of course the national and international providers and the NRENs, so ESNet in the US and all of the NRENs in Europe. However, it's not all perfect. There are some times when we have problems. It's only now that we're getting the basic monitoring that looks towards the users. I understand that there's lots of network monitoring, but actually from the user point of view, it's very difficult to understand if your data flow is not getting through, whether it's a problem with your software, a problem with the link, or a problem with the network itself. And actually, even when you determine it's a problem with the network, it's still a non-trivial issue to understand what's going on. So if there is a problem between Italy and New York, and the physical problem is in Vienna, who is responsible for following that up, and who is responsible for telling me that the problem is fixed? Well, it seemed that nobody was, or nobody felt as though they were. So there are still, I think there are still things to understand and still things to iron out here. This is not a problem that happens very often, I hasten to add, but when it does happen, it's a real nuisance. So I think there are still things that can be improved in this area, but we're starting to get there and starting to understand what the problem actually is. And the other thing is, I think this doesn't come for free. We spent, what you see on this timescale is the history of the testing that we did, and there was an enormous amount of testing. We spent something like 6 years getting up to the data rates that we were able to sustain now. So the fact that we're able to do it now in a relatively easy-looking way is due to all of this testing. And this was a non-trivial exercise. It meant we had to go almost link by link and point-to-point connection and validate each of those. And this we continue to do. So part of the data flows that you see on those data transfers are background testing. So there is, even if there's no real data flowing, there's always some testing jobs making sure that the network connections or the point-to-point connections are really at the level that they should be. And I hear comments from other communities that have tried to do similar things that haven't gone through this testing. It doesn't just work. If you have a point-to-point connection between your lab and somewhere else, and you try and send data at some huge rate, it doesn't just work. You still have to put in significant effort to debug that and make it work in the way that you need it to. And I think that's something that we have to bear in mind when we think about all of these new technologies coming and all of the potential that we have, is that actually validating and make this work in real application land is still something which is hard. Okay, so just then switching to the physics, just to give you a flavor of some of the successes. I mean, it's often said that all of new experiments have to basically rediscover existing physics before they can look at new physics, and this is exactly that. This is an example from CMS. So on the top you see the original history, which starts in 1933 with the discovery of muons and goes up to the top. And this is the sort of CMS timeline, starting in 2006, when they first switched on some of the basic parts of their detector and rediscovered muons. But then most of what we today call the standard model was discovered in the several months of 2010. So really they went from basic physics in early 2010 up to the top already in the middle of 2010 last year. And so they're now at the point where they're understanding their detector, they understand that they can reproduce known physics, and they start to feel confident that they're able to look at new physics. So this is just then some hints. I'm not claiming this is new physics, certainly, but we start to enter a new regime. And just a couple of examples. This is the highest mass two-jet event ever observed. This is a candidate for a W and Z co-production. And this is from heavy ion collisions, is what's called jet quenching. Normally, when you see two jets, they're equal and opposite. But in this case, one of them has been absorbed by this quark gluon plasma, all of the matter that's inside the nucleus in these very dense collisions. So these are all new things. This was a subject of a paper at the end of last year, and clearly there is more to come. So some of the successes we had, then we have really a working grid infrastructure. The experiments really have distributed models. It's enabled the physics output in a very short time, and I think this is one of the key points. And it really is a very short time. It's a timescale of a couple of weeks from data taking to physics being produced, and this is unheard of in this field. The network traffic, as I said, is in excess of what we'd planned, and the network is extremely reliable. Significant numbers of people doing analysis at the tier 2s and not at the tier 1s and tier 0s as people had feared. And in 2010, we had lots of resources, but now we start to see them full. And so this is potentially a problem to manage. And the support levels were manageable, but only just. And this is something that we have to address for the future. So just a couple of words on the computing model. You've seen this several times. This is the hierarchical model that we designed more than 10 years ago. And I think one of the keys here was that there was certainly a fear that the network would be a problem, that we wouldn't be able to really achieve the data rate. So a key feature of this was really moving the data outwards and placing it carefully at each place. And that was built on the E infrastructures that today we call grids. There are many examples of this, EGI, EGE before it in Europe, Open Science Grid in the US, and then supercomputer grids and so on. And essentially the grid, as we call it, is the middleware layer. It's the software that enables us to bring these things together. And if you look a little bit more detail in what we actually did, there's actually quite a lot of it, and it's quite complex. And data management, of course, this is very important for LHC. Security, and by security I include the authentication, authorization, the whole X509 infrastructure and so on. And that part is one of the very valuable things of this. But there are also other things, information services, job management. And I think one of the things that has to be remembered here is that the experiments themselves invested an awful lot of effort into integrating their software with this complex stuff and making it work, and actually hiding that complexity from their users, from their physicists. So actually the physicists see the experiment framework and really know nothing about the complexity behind it. And I think that explains why so many people have been able to use it, because they don't actually have to interact directly with it. So we've learned a few lessons in this year. These computing models based on this sort of hierarchical model relied on data placement, as I said. Jobs were sent to data sets resident at the site, and the data had been pre-placed there. So we ended up with multiple copies of data hosted across the infrastructure for fear that some of it wouldn't be accessible. And I think underlying this was a concern that the network would either be insufficient or unreliable. However, it turns out that a lot of data has been placed at sites and was never touched. And refreshing these large disk caches uses an awful lot of networking. And as I said, the network itself, for us, is extremely reliable. So it's much better to be able to use the network than to... okay, I'll come back to that in a second. So we start to change the data model. The data placement will now be based on dynamic placement where jobs are sent to a site. Essentially, the data is sent to a site when a job requires it, or just before it requires it, in fact. But also popular data is replicated, whereas unpopular data is probably either removed or just not sent in the first place. And this means that this huge disk cache that we have becomes much more dynamic. We also start to think about using remote I/O to the running processes. Now this can be in several ways, either fetching a missing file from a data set. So a data set in these cases can be tens of thousands of individual files. So fetching one single file remotely actually makes the whole thing for the user appear much more effective, much more reliable. We also like to start reading files remotely over the network. And actually this turns into somewhat less network traffic now than we saw last year. And that, I think, explains some of the reason for the apparent decrease in the data that's moved in the early months of this year. So we start to see the computing models evolve from the strict hierarchy to what we call a mesh, where data can be accessed by any tier 2 from any other tier 2, or indeed from tier 1s, or indeed from CERN. And so this clearly has implications for the networking. And so I'm sure you're all aware that there's the concept of what's called LHC1, which allows, or is intended to allow, the easy connectivity of tier 2s and indeed tier 3s, which is a sort of lower level of site, to connect to any tier 1 or tier 2 without overloading the general purpose backbone infrastructures. So this is not intended to replace the OPN at all. In fact, it's intended to be completely complementary to it. So there are some other challenges. I mentioned the resource contention, so the experiments really have to work hard on making more effective use of the resources that they've got. It's difficult. I mean, multi-cores are very difficult to use. And we already start to see that the physics reach is potentially limited by the resources that they have. And the increase in resources in itself is limited by funding. So this is a significant challenge for the experiments. As I said, we're starting to change the models to be able to more effectively use what we have. The data management is evolving, as I said. The network model itself is also evolving. But we'd also like to start making it easier to access for people. So we have this X509 framework, which is quite complex and has some security implications. And I think there's a general feeling that it would be much simpler for many people if they could use existing identity management schemes and be able to use their existing identities to have access to this infrastructure. So there's some work starting on understanding what's feasible in that area. But the other area that we have to worry about is the sustainability and the ease of maintainability and the ease of operation. So these are big issues that currently cost a fair amount of effort. Grid middleware is complex, as I said. It's probably more complex than the model of computing that we now have. It's also not the right buzzword anymore, so we have to understand what we really need from it. The sustainability of operations is important to us. The more we can simplify the middleware, the more we can simplify the software that we're running, the less people will need to do that. And it's far from obvious that commodity hardware at the scale that we're running is reliable enough, and we need to understand how we can improve that with software. So there are a number of activities in all of these areas. But we also recognize that technology is changing. Clouds is the right buzzword now. But there are many other things which people are interested in for sometimes good reasons and sometimes not. But I think a general theme here is that we're trying to move away from special solutions that we have to maintain ourselves. The other thing that I think we start to learn is that we didn't really understand what a distributed infrastructure was. We knew it was connected by a network, but we really didn't understand how to make the best use of that. So I think what we saw in the model that we've had was that many services were replicated in many places unnecessarily. So databases, the data placement you've seen. And I think underlying this was a lack of trust that the networks would be reliable. And this, in turn, increased the complexity of the middleware itself and the applications. But now we see a move towards centralizing these again. And it's clear that if you have a failover copy of a database in one other place, it is much simpler, and it's much simpler to manage and understand what to do with it than having a database schema which relies on a distributed database and the technology that goes with making a distributed database. And that is a very good example of something that we're simplifying. And clouds, I can't not mention. The reason we have a grid is because we need to collaborate and we need to share resources. And so no matter what we do and no matter what technology we employ underneath, we will always have a grid. And our network of trust on all of the security infrastructure that goes with that is of enormous value to us, and I don't think we want to lose that. And I think it's also of enormous value to e-science in general, because I think this is one of the things that allows people to collaborate across these infrastructures. And I think that probably should sit on top of the pile of as one of the major achievements of this 10 years of work in grids. For LHC, we also need distributed data management, and then we have to support the very high data rates and throughput. So of course we will have to continue to invest effort there. But for the rest, I think this can start to be more mainstream now, either from open source or commercial providers. For instance, we start to use message brokers more and more as inter-process communication instead of the very specific and strange things that the grid world used. Virtualization of our computer centers is already happening, has gone quite a long way in some cases. So it asks the question, can remote job submission, which is one of the job management functions of the grid middleware, can this now be more cloud-like? And there's certainly huge interest in using commercial cloud resources, especially as we start to see our own resources become full. And so actually this is the time to start asking the question about what's this going to be like in the future? I mean, how much longer do we have to run our own infrastructures for? And where is the point at which we can actually start buying these services? Well, clearly we're not there yet, but I think we have to start thinking about these things. So just to finish on a final challenge, what we need in terms of connectivity is not just bandwidth. We are a global collaboration, but actually you have to reinterpret global as to those places which are rather well connected. And clearly the better connected countries do better. And one of the things that we have to address in the next few years is how to allow all of the other places that really want to participate in this, that want to be part of LCG, how to allow them to connect effectively as well. And there are huge communities, real communities and potential communities in the Middle East, in Africa, and in other areas, but also not to forget on the edges of Europe, which sometimes have a very difficult job in connecting to and being effective in this infrastructure. So, I mean, things are changing. So people don't have to have the data on their desktop. They could be remote consumers of the data. They can do analysis remotely. They don't have to download it. And I think there's also a huge opportunity coming with mobile devices and netbooks over GSM. For example, I learnt a couple of weeks ago that something like 80% of the population of Africa has a mobile phone. So there's a huge potential for using these things to actually participate in science. And there are actually science communities there that do want to participate, and we have to accept the challenge of how to connect them. So just to finish, so I think the conclusion here is we have built a real distributed infrastructure. It really is successful. It does deliver science very quickly. The experience in the last year has started us thinking about new ways to do this in the future, and I think the key to that will be the evolution of the network itself, and certainly the evolution of the way we use the network. Thank you.
Thank you very much, Ian, for this excellent presentation and overview of what goes on at CERN. We have time for a couple of questions. We have one there in the middle.
I am from Kazakhstan, so I am representing Central Asian NRENs. So I think our scientific and research institutions want to be a part of this large project. How to participate in that? How we can do that?
How to join the LCG. So
yes.
I think a physics institute just has to send me an email. We can start the discussion. So one of the first questions will be, what's your connectivity? So then
our connectivity, as far as I know, our Central Asian NRENs part of the current project. Current project,
yeah.
As far as I know, started about STM connection from Hamburg to Almaty. So it's from the beginning of the next year, from the 1st January.
I think we are open. We're very open to anybody collaborating. So the physics groups should send me an email.
Okay. Thank you.
There's another question down here.
In your last slide, you just mentioned that there are big opportunity with mobile device, netbooks, and GSM. So I wonder if you have some example of such opportunity for high energy physics. What do you have in mind behind that?
I don't have an example. It's a thought. I mean, we have a network, right? The data is available. So if you have a netbook, essentially you could do physics analysis. You need some way of looking at the data, right? So if you're not on a good connection, the GSM connection maybe is sufficient to allow you to have access to the data. You don't have to download it to yourself, but maybe it's enough to give you access to the data which is somewhere remotely and allow you to do some physics analysis on that. I think all of these options should be looked at to allow these remote communities to participate. And I mean, maybe LHC is not the right thing, but there's certainly other sciences which may be interested in this.
Good morning. Gioacchino Buscemi, European Space Agency, Earth Observation Department, Network Security Officer. I'm interested in the amount of resources that you allocate for the network and the possible budget, if it's possible to know.
It's impossible to know. It's not done in that way. The network, well, I mean, the OPN is, I mean, the connected sites pay for the OPN connections. But if you're talking about the whole network, this is part and parcel of the cost in each country. And those costs are not really exposed at a higher level. So we don't account the cost. When a country signs the MOU to join the collaboration, it guarantees to provide a certain level of resource, a certain level of bandwidth, a certain quality of service. And how much it costs it to do internally is its own business, and we don't look at that. So it's impossible for me to know an actual cost, either in terms of money or in terms of people.
We have time for one more question in the back.
Hi, Giovanni Moura from the University of Twente, Enschede in the Netherlands. I'm just curious about the data, how you share the data in your network there. Like any research institute all around the world can get the same data, or someone in another place can get the data or it's classified. How does it work?
So you have to be part of an experiment to get the data at the moment.
Okay.
there is a big move to open access, but open access to the data, I mean, you know, the data is there, but it's very difficult to do anything with it. It's very difficult for the experiments themselves to do anything with it. There's an awful lot of metadata that you have to understand, and that metadata is not necessarily metadata that's in a database somewhere. So it's not, I mean, it's not even a question you can easily ask is how to access the data. However, there is, I think one of the things which many science institutions are looking at is how to make data more accessible and more open. But this will start from the other end of the chain. It starts from the level of the publication and will start to move down to the data sets which were used to plot make the plots in the publications and allowing access to those, and that will gradually move down. But this is going to take some number of years to achieve. But this is certainly something that people are looking at and worrying about. Yeah.
Okay. So I think we are running out of time, though I would like to have the privilege of asking you just one more question. I've had the privilege of working with CERN a few times on this and been part of the networking community, assisting and building the infrastructure for this. And I've been time and time again impressed by how effective and how well organized the physics community is. So my question is what you're doing applicable to sciences in general, or is this really something that only works at CERN and for physics because physics is organized uniquely?
Physics is organized uniquely, yes, that is certainly true. But I don't think what we do is unique. I think it is applicable. I think it's certainly true that some of the technologies, the grid technologies, are not terribly usable in other fields. That's certainly true, and I think some effort needs to be invested there. But I think probably LHC or high energy physics is a unique community. It's had a long history of being a very tight community. So it was relatively easy for us to work in this way. It wasn't true of the computer centers. So for the physics groups, it was true. It was much harder work to get computer centers to work together and trust each other. And there was some significant effort there. So I think that experience could be useful in other areas. I think it depends on the community, and other communities have very different needs. As I'm made aware continually, this is not, there's no one size fits all here. But I think we have some lessons that could be useful, yeah.
Okay. Thanks very much, Ian. So our next speaker is Andrew Cormack. Andrew is the Chief Regulatory Officer at Janet, and he works there with regulatory issues, security issues, policy issues. He was formerly the head of CERT at Janet, and he will talk to us about what makes a community, how to support a community, how to create them, and he's promised us to celebrate some of the successes that the NRENs have had in that space.
Yep.
So,
okay. Thank you, Lars. I'm not sure if Lars's last question was deliberate as a link, but I think it makes a very nice link to what I want to talk about, because when I saw the title for the program, the theme for the conference, and it was about communities, that got me thinking, how do we build communities? How have we built communities in the past? Are there challenges to that in the present and the future? And as Lars said, a bit of celebration, a bit of challenge, which I hope is what a plenary talk ought to be. If you look at literature on communities, I've been rereading Larry Lessig from 10 years ago. It's absolutely fascinating on what he thought was going to happen to internet regulation. And he was right about the dynamics and the groups that would be involved, and he was absolutely wrong on the technology, which is great. He talks about architecture, law, and norms as ways that societies regulate themselves. I've translated that a little bit into BRICS rules and generosity. So what do I mean by that? Well, BRICS is our community is all those who have the same technology as us. So there is a community of Apple users, and there is a community of PC users, and never the two shall meet. that's a BRICS example. You know, they may have nothing else in common, but if you see that logo, that is my friend. The second type is rules. So I form a community with anybody who lives by the same rules as I do. So there are communities of countries. Those are externally imposed rules. There are also communities of internally imposed rules, the ways I choose to live. I will associate in a community with other people who choose to live the same way. And then there's generosity, which is, I'm a nice person, I will be a community with anybody. And actually, that is, to a large extent, Ian mentioned open data, open access. That's very much a generosity. You know, I believe in openness and giving stuff away. And that's just how I work. And it doesn't matter who you are. You can be part of my community. So in the real world, just as I'm a mathematician, so I tend to start with the extreme examples to understand what's going on. The real world, we have BRICS-only communities. And we built these, most countries built them in the 1950s, 1960s, 1970s, and we called them homes for heroes, or we called them machines for living, and they were all positive, and they were going to create, by their architecture, perfect communities of everybody who lived in them. Unfortunately, late 70s, early 80s, 90s, we discovered actually we don't like that architecture. We don't like being forced to live in the pure clean air on the 18th floor if the lift doesn't work, elevator. So it goes from being a home for hero to being a sink estate very quickly. And once it's got to that, once you decide you don't like the architecture, there's really only one thing you can do with it. And where's the community now? The community is a pile of bricks, and there have been huge social problems around making that transition from a society that, or a community that was based purely on an architecture to a community that was based purely on, or was based on something else when you destroy the architecture. Note my little icons, I'll come back to those. Rules only. We're in Prague, so I had to include Kafka. The trial is about, I interpret it, it's about a community that is regulated by rules. The catch is that you don't know what the rules are. You know when you've broken them, and you're put on trial, and you still don't know what rule you've broken, but you were told you've broken the rule. And it turns out that doesn't work very well either. However much we might say we want to live in well-regulated, well-ordered societies, actually, if the ordering of the community comes back and bites us, we decide maybe we didn't like it after all. So that's a rules-only community. What about a generosity-only community? I loved this. I had to put this in once I discovered a sculpted parsnip. I have never seen a stone-carved parsnip before. This is gorgeous. This is a memorial to a fascinating group called the Diggers, who in the 17th century were, I've seen them described as Christian communists. They very much believed in all property being held in common. They believed in working for the general good. They went off and they found, it seems ludicrous now, a patch of unused wasteland in Surrey. Anybody who knows the UK knows that there is now no wasteland in Surrey. It's all very expensive housing. And they dug it up and they started planting, according to the memorial, I think it's parsnips and carrots and peas. And they got on well. They got on very well, and it all worked very nicely until the neighboring landowners started getting worried that the diggers were being so successful that the serfs, the tenants, the people who were being forced to work their land would start seeing this was attractive and say, hey, we want to live like that. And the diggers were eventually broken up, actually essentially by a heavy mob sent in by the jealous neighbors to say, stop doing that. So although again, generosity sounds great, you do have to be careful that it might upset people. You might break other people's economic models by doing a generosity-based community. So what's the fundamental problem? Well, it's people. For all we say we want to be well-ordered, for all we want to say we want things to prevent bad things happening to us. We want bad things to be impossible. And we like to think we're generous. Actually, if you rely on any one of those models, people also like freedom. They like flexibility. They like the ability to do stuff that maybe hasn't been predicted. So you have to somehow come up with an architecture for a community that allows that bit of flexibility. So my first conclusion is very much using a single mode only, one of those three, is going to be fragile. And when it becomes unacceptable, it collapses. You've got nothing else. So the community fails at that point. And looking at the real world, it's much, much less tidy than that. It's a complete mess. But by observation, it does manage to support communities. So what do we do? What can we learn from that? The NREN community. I should have been counting how many times I've heard that phrase already this week. We know it exists. It's here in the room. It's also somewhere out there on a video stream. You know, the Terrainer conference community isn't just the people in this room, in this hotel, in this city. What about us? What do we do? We're good. We are very, very good. We have done stuff that has changed the planet, mostly in good ways. For example, preceded by a speaker from CERN. Scarily, I was reminded that on my first day working at Cardiff University, my job description was, there is something called a web server. We think the university ought to have one. Please find out what it is and make it. That was 17 years ago. The whole web stuff has happened since 1994, even in education. You know, we all say, oh yes, we did it first, and then the world heard about the web and the internet. Now, even in education, significant universities didn't have web servers in 1994. We had Gopher. Anybody remember Gopher? Thank you. Good. Yes. That's the reverse of the question yesterday for anybody here under 40, by the way. We're good. Shortly after we invented the web, we discovered we had to invent incident response. Bad stuff started happening, and we very quickly learned how to respond to incidents happening across networks. Nowadays, the form of incident response and security teams. All these logos used with permission, except the ones that are used under license, by the way. We do fiber. You know, the basic technology that we use to move stuff around actually comes out of education, mostly. We had a presentation at our net workshop was it last year, I think, by somebody who is researching fiber. And I really hope the copyright industries weren't listening when he talked about just how many movies you could ship over one strand of fiber in a very short time. Don't tell them. The capacity of this stuff is amazing. I'm literally mind-blowing. I cannot conceive of some of these numbers. They're on a par with the numbers Ian put up. Video conferencing. Actually, this image makes its own point, because I wanted an image of a large video conference. And I searched on all of our licensed image stuff, and I searched on all the web, and I couldn't find one. And I had to look within the NREN community to find a picture of this sort of multi-point, large room video conference. The outside world doesn't have pictures of it. So we're good at that too. Eduroam, superb community. I was slightly alarmed yesterday because it was Monday morning. I have been told I must turn off data roaming on my mobile phone because it's really, really expensive. So having spent the morning wandering around the city of Prague and come back to the hotel, I panicked somewhat to discover that my mobile phone had synchronized. Oh dear, have I run up a large bill? No, somewhere in the city it found Eduroam without my involvement. It logged in, it connected, it got data. Superb. Again, a global network, a global community that we have built. What tools do we use on these? Well, the web, I'd suggest, is technology from CERN, and then, quite explicitly, the generosity not to license it, to give it away. Say, this is for the good of the planet. Very strong generosity, which is the whole basis for the success of the web. Incident response, again, I think almost entirely generosity. Why should I help you fix your problems with security? Well, because one day you might help me with mine. No, it's a straight exchange of generous gifts. Fiber, pretty much pure technology. Some of it is then commercially exploited, some of it isn't, but it's a technology-based community. Video conferencing, again, technology generosity. We have big central switching services, support services. We're talking about cross-European video conferencing, making that easier, because it's the right thing to do. EduRoam, I think. Yes, EduRoam. Very much generosity. It's all about universities saying, actually, I'd like to give a service to visitors. Bit of self-interest, because then you don't have to connect those, you don't have to go through the hassle of giving those visitors accounts. But it's mostly generosity, and certainly we're very grateful for it. And at last, my little rules icon has turned up. There is an EduRoam policy. And certainly some of the universities connected to Janet that we spoke to about EduRoam would not connect until they saw that policy, they understood how it would work. So, rules are starting to sneak in. But if you look at how we naturally do stuff, our natural ways of forming communities seem very much to be around technology generosity. We don't like rules. Believe me, I have spent the last 10 years trying to sell you rules. It's trying to give you rules. I'm generous. Here are rules I think you need. It's much, much easier to come to you lot and say, here's a cool new piece of technology, than to say, here's a cool new policy. I bear the scars of that. Actually, it's worse than that, because some people in this community, when they see a rule, will kick against it, will actually actively go out of their way to stretch it, to bend it. They wouldn't say to break it. We're very rules resistant in this place. But I think in the last, actually probably only in the last year, I'm starting to see projects suffering from the lack of rules, saying, our users of NREN aren't the same as your users of NREN, and our whole community assumes that they are, the way we have built a service. The purpose of our NREN isn't the same as the purpose of your NREN. Do you only connect universities and colleges? Sorry, do you only connect universities? Do you connect universities, colleges, colleges, schools, universities, colleges, schools, libraries, health service? No, different. And we're starting to see some friction there. One of the issues around video conferencing is that the service offered by different NRENs isn't the same. So users quite rightly expect stuff to be the same wherever on the planet they are, and they suddenly discover they're in a country that doesn't have a central video conferencing service, and they say, why not? We've set their expectations. So I think we're hitting some scaling issues with this, where actually the pure generosity, pure technology issues are starting to be a problem. Because what is the NREN community? It's definitely them. We all know, it's people like Terena and Janet and Cessnet. They're definitely the NREN community. What about this lot? Universities, research, colleges, schools? Yeah, probably. Museums, local authorities, health? All right, so that's the NREN community. Except I asked around and I said, look, who do we actually connect to Janet? Who do we have private peering arrangements with? Because these are organizations that we believe are so important to those people that they ought to be helped through Janet to get access to those. And then you start discovering all sorts of people. Are those the NREN community? Some places, some people, some situations, yes, very much so. These are certainly the people who can send packets at very high speed and in very high volume, exchange them with all the others within the blob. So this is where I think that friction is starting to come from. We thought we were building and watering a beautiful flower called the internet. And I wonder if we're starting to realize that we got a cactus. It's not quite as friendly and as nice, and everybody plays the way we do as we thought, hoped it might be. So I think my first challenge to you is understand this. Possibly be a little more aware that things might not be the same as they are at home. And are we actually limited, are we restricted only to those communities? Are there other communities that we may want to get involved with, or they may want to get involved with us? This is us, the blob from last time reduced. Ian mentioned netbooks. How many people here use a network-connected device as part of their job, and how much of the time is that stuck to an NREN? How much of the time is it dependent on a commercial 3G network, an ISP network at home? I telework. BT is very much part of my working community. I might rephrase working community on occasion. All these devices, for symmetry, I haven't put clouds in here, but there's quite a lot of UK universities, and I think elsewhere, outsourcing what look like key community functions: email, calendar, data storage. It's not on the NREN anymore. So we need to start seeing those organizations as part of our communities, the providers, maybe even the device manufacturers. Do you want a really clever e-learning application, or a network monitoring application, or a physics application? You've got to talk to an application store. Does that make them part of our community? In some cases it will. Governments, we may not want them, but they certainly want us. They look at us and they see big, fast, expert, national, reliable networks. Cheap, certainly by the standards of government networking. They want to talk to us a lot. That's challenging. I spent quite a lot of the last year talking to them. It's interesting. I'm going to spend a lot of the next year talking to them too. Money. We don't do money. We're generous. We give stuff away. Except in England, students will be paying between £6,000 and £9,000 a year for their education. So even members of our community are doing money. They want to sell stuff. They want to sell their expertise. They're being told by governments to sell their expertise, certainly with us. Universities must go out and make more money out of their technical knowledge, their new discoveries. Money is suddenly an issue around NRENs. Not money to fund it, but are NRENs up to having economics inserted into the set of rules? And of course, we're a big wide open community, so this lot exist. Both of them, mostly. We built an open network. We built a network, I think Kees de Laat yesterday described it as what it has become, a network for the world. And the world has both bad people and people who lock up bad people in it. So we shouldn't be surprised when they come and say, we'd like to be part of our community, your communities. And indeed, when people in our community say, how do I talk to law enforcement? There's a community we need to build around there as well. And these are different. These people talk very differently. They say different things, scary things we've never heard before. Cybercrime. And we put E in front of anything. Everybody else puts cyber in front of anything. Buzzword compliance. If you're talking within NRENs, call it E something. If you're talking outside, call it cyber something. Cybercrime, we haven't. Ooh, have we built a network that can be used for bad things? Seems we have. Compliance. Scary word. But it's what's expected out there, which is going to be coming here. And compliance is all about rules. And remember what I said about rules and us. Economic forces, I've mentioned issues around money. Soft regulation, informed self-interest, doesn't sit very well with the generosity strand. We are supposed to restrict what we do in our own interests, but our interests are to give stuff away, we think. That's the way we think. The last 2 or 3 of those then bring up nothing, network neutrality. I don't know why I'm pointing at that screen. This is very, it's a built-in reflex. You point the changer at the slides. Network neutrality, what does that mean? Aren't NRENs neutral networks? I think they are, having been involved in the net neutrality debate in the UK, at least, as we understand net neutrality. But are the networks that we then rely on to get stuff to students, to researchers, are they neutral? Or is our nice physics research app, sitting on an iPhone or an iPad, suddenly going to discover that the mobile network it connects to doesn't support that protocol? Challenges we suddenly have to deal with. Critical infrastructure. Some countries, NRENs are regarded as part of the critical national infrastructure. Not yet in the UK. And that brings all sorts of people sniffing around saying, how resilient are you? What are your, what was it we had? Which side of the door are the screws to get into the network operations center? That's the way they think. We don't do that stuff. We may have to. And the best one, of course, the kill switch. How do I turn it off in an emergency? Has been asked at very, very high political level. Where do you start to explain to somebody who thinks there might be a kill switch on the internet? And their preferences are very different from ours. They tend to like prevention, not cure, law rather than compromise. Very interesting. I was asked to go and talk to a critical infrastructure group in another country a few years ago, and sitting around a small room with a group of people. And I always start by saying, can you tell me what your name is and what your organization is and what your role is there? And I was told, you can't do that. You're not allowed to know who they are or where they're from. Right, that changes my style somewhat, cramps my style somewhat. They go for contention and congestion. Ian's worried about congestion. Commercial networks think contention is great. That's efficient. That means we are using our network to the best use. It's just a different mindset. We talk about over-provisioning. I think you'll find any commercial network will look at you as if you were start raving mad if you say over-provisioning. Why would you pay for more than you need? And certainly centralized rather than distributed collaboration. One of the more enjoyable days in this job was giving evidence to the House of Lords. What was it? For those who've seen Yes Minister, you will be proud to know that there is indeed a Home Affairs subcommittee of the European Affairs Select Committee of the House of Lords. And it really exists, and they invited me and a guy called Chris Gibson, who is involved in incident response at Citibank. And they kept coming back to, where is the central authority? Who runs the internet? Who fixes the problems? And we kept saying, there is none. It just works. And I eventually got frustrated, and I said, look, Mr. Gibson, you're a bank. Heavily regulated industry, very good at secrecy, protecting information, everything done by processes and stuff. Mr. Cormack, you're a universities network. I'll take the rest. How do you two talk? And Chris just said, I know his phone number. And they clearly could not understand that way of building a community. That we just do stuff because it's the right thing to do. We know each other. We've been to nice foreign countries and we've sat around over a beer. And it's incredibly powerful. It's just not a method that others don't, that others recognize. We could ignore all this. We could say, go away. But then you'll find that your network is being controlled, being regulated by people who write things like this. This is from the minutes of the European Union Law Enforcement Working Party from mid-February this year. There will be a secure European cyberspace with a virtual Schengen border. My immediate reaction is good, that leaves us out. It's going to be a bit of a pain having to open all my packets and remove the laptops and the liquids from them when I want to cross the channel, which I think is what Schengen does. I was really optimistic when it was announced you were thinking of suspending the Schengen agreement. I thought it'd suddenly be much easier to get through Amsterdam, but apparently it isn't. It's not how it works. This is a documented conclusion of a European working party, which just completely misunderstands the internet. So I think we need to engage. And that's the next challenge, is we've actually got to help people understand how the internet works. Back to my picture. This is multi-mode. Why? There's some technology. Hidden behind all the heads there are curbs at the edge of pavement. They don't actually stop cars driving up and onto the pavement and mowing down pedestrians, but they give the driver a clue. So there's a bit of technology there. There are rules. Hidden up in the top right, there is a sign that says no vehicles. Oh well. Traffic lights are rules. I'm not sure if these are turned on or if it's just the sunlight means you can't see whether they're on. But there are rules, there are symbols to remind us of rules. And there's actually quite a lot of generosity. That woman is not going to get run over by the bus, no matter how tempting it might be for the bus driver. We're relatively generous to jaywalkers, at least on this side of the Atlantic. So we need, I think, to work out multicultural ways of building communities. We need to understand how to combine these modes of community building in a way that gives the flexibility for different participants to feel comfortable that they have something they can live with. So far, I have to say, the examples of this, the history of trying this isn't good. When I hear that anybody is going to legislate for the internet, I think I'm now at the stage that the best I hope for is it's ineffective. It doesn't actually cause harm. Not a good place to be. The Commission are very keen on an information society. They've had a directorate for it for a long time. Have we got one? Do we have a happy, multicultural, productive, community-supporting internet? Or does your internet look like that? I confess there are days when my inbox does look like that. Full of graffiti, bits of vandalism, attempts to defraud me, so far none successful, with nice big metal grills to stop bad stuff happening, called firewalls and antivirus scanners and stuff. That's not a very good picture of the internet, but how do we get away from it? Do we say, yep, the internet is a tough place, you've got to look after yourself? Or do you say, here is a garden with trees and flowers and lakes and everything is lovely, just don't go over the wall? Or do we say, actually it turns out this thing isn't good enough for real work? Shame, but get on. It's good for playing games and for Facebook and all that sort of stuff. But real use, maybe not. Or do we try and help the planet make things better? A couple of models have been suggested. There's a public health model, which is being sort of run around to see if anybody likes it. This is a rather fine grade 2 listed Victorian asylum. Do you want an asylum or a hospital? A hospital is somewhere where you are allowed, well, a hospital is not somewhere where, a hospital is there because you are allowed to wander the streets as much as you like, do whatever you like, until you have a communicable disease. And at this point, if it's a bad enough communicable disease actually by force, you will be taken to a hospital and you will be made better, so you are no longer a threat to the rest of the public. Or is there a risk that we build what this place actually was, which is a place where you are a problem to society, we will put you in a relatively comfortable environment where you don't notice that you can't get at the next Skype or the next Facebook, because those aren't allowed inside the walls. And I'm worried, actually, that for the majority of the internet population, that might look quite attractive. And then you've got self-inflicted network non-neutrality, which, if you think, as I do, that the internet isn't yet finished, there is still new, exciting, unknown stuff to be done with it. That's horrible, because that puts us back to the old model of you can only develop things with the permission of the authorities. And that kills it. As a progressing, developing thing, kills is wrong, it fossilizes it. It keeps it exactly where we are. So I quite like this model. There's a problem as well with who pays. If the person who discovers that you are infected has to bear the cost of you being made well, that, I'm an NREN person, I don't do economics, but I can do that much economics. I'm going to forget that I discovered you had a disease. I think Germany and South Korea, the governments are either looking at or have set up central hotlines, so an ISP can discover from its traffic data that there's a problem with this PC, it's part of a botnet, it's got a virus, it's spamming, whatever. And the ISP can then give the customer the number of a centrally state-funded help desk to clean up. So the ISP doesn't carry the cost of doing the cleanup. And that's sort of how we do things in the health model. That might work. But as I say, you have to be a little careful of creating this nice, cozy, padded cell. Comfortable padded cell. Another model that's been suggested is the pollution model. Well, no, sorry, it's an anti-pollution model. It's how we think we're going to deal with pollution. That everybody does the relevant bit. Polluters try and make their technology less polluting. People who haven't yet got to the point of polluting develop along another path, so they don't do pollution at all. And we all change the way we work, the way we live, to do a little bit. And I think here the idea is everybody does a little bit, and the world gets better. That sounds wonderful. That's a really NREN way to do it. Except if you look at the history of global climate change conferences, we don't seem to have got the hang of it, even at the level of rather fine petrochemical refineries just outside Edinburgh, that one. So maybe we don't know how to do it. So my final challenge is, how do we continue to build systems that support the development of online communities? How do we get to a point where, and not just us, how do we get to a point where the world sees this as a source of raw materials and not a scrap heap? I think it's a huge challenge. We've led the world in many cases in how to use the internet. I'd love to think we could continue to lead the world in keeping the internet habitable, usable, community building. Thank you.
Thank you, Andrew. We have time for a couple of questions.
Yep.
We have one right here.
Yes, can those with questions please start asking in the order from where the microphone is?
Okay, Andrew. Actually, Facebook, LinkedIn, and Twitter demonstrated quite successful creation of community.
Uh-huh.
So my question is how it's related to the explain or describe the generosity model used in NRN. And maybe another question is what like Facebook size initiative came from NRNs, except maybe from Doodle that I heard about this.
Remind me where Facebook came from.
But not from NRN.
Came from Harvard. Go and watch the film. Or indeed read the court case.
Yeah. Actually, Facebook was a private initiative and actually quite
I
insulting
got the wrong one,
privacy. So this is not NRN.
I think, but the idea of social networks certainly did. Virtually all the search engines originate in universities.
Yes,
Yeah.
but Google was actually was asked to move from Stanford.
Yep.
And after a few years, they created a commercial. So this is something tricky how you can treat.
I don't see any problem with that. I mean, that is an organization that has managed, actually from reports I hear of how it works internally, hasn't actually changed its culture internally that much. I gather it still feels pretty much like a research lab where people go and have fun and generate fantastically valuable product. But they have certainly changed the style of approach to the outside world. Maybe. You know, Google don't do evil. Well, that kind of sounds like pure generosity to me. How we build the next Facebook, I don't know. If I knew, I'd be doing it and investing in it. But what the internet gives us, I think, is the possibility that me, as the NREN, doesn't have to know. You know, if you have a good idea, get on with it. You don't need my permission. And I think that's the thing we have to somehow try to protect, even though exactly that freedom also allows the bad guys to think, how do I develop distributed denial of service attacks? It was fascinating being at the first conference in Chicago about 4 months after the first big DDoS attack on, I think it was eBay and Amazon. And everybody there went, yeah, that's obvious, we could have thought of that. The internet let somebody think of it, do it, and it's still going on. You know, the good guys haven't, you know, we're getting better at cleaning them up, but that's an internet arms race. And it's the power of the internet, it lets that happen. And if you try to build an internet that stops that happening, unfortunately, it will stop the good innovation too. So I think that is inherent in the internet culture, that for the internet to work the way it does, it has to be that way. And that's probably a message that we have to get to those outside our community, that, sorry, if you want what Jonathan Zittrain calls is the generative internet, the internet that is capable of creating new ideas, new tools, new ways of doing stuff, it has to be an internet that can create new ways of doing bad stuff as well. It's just, you can't have one without the other. So, probably didn't answer your question. Thanks.
One more question. No? Well, I have one. So I kind of like what you speak of as the generosity of the NREN community and our community. I like the values we share and the way we operate in many ways. I also realize that you make a very good point that the world is becoming more complex and we can't just go on operating like we did because there's new demands, new challenges for us. So how do we meet those? How do we go along responding to those new demands and still keep on having the values we used to have and keep being generous? Can we do that, and what's the path for doing that?
I think what I try to do, and actually where most of the policies I'm trying to give you come from, are when I see a new, as part of my job within Janet is to look at new developments. When I look at a new development, I think, what would the policy for that be if we needed one? Or, you know, if it's whichever mode isn't there, you know, possibly might there need to be other technologies in there that aren't there for the main function, but when it leaks out into the rest of the world might be needed? And at least be aware what they might be, possibly build them in. That's even better. Now, if you can deliver something that is ready for those external challenges, but still works the way we work. Now, I'm not saying we have to work differently. I'm saying we have to be aware that others do. And our products need to be fit for their world as well as for ours. So.
So we have to think about it earlier.
Yeah, that's my job. I hope we have to think about it early because that's what they pay me for. So.
So thank you very much, Andrew.
Thank you.
So before I let you go, there's a few announcements. There's still demos going on in the breaks. I encourage you to go and visit all the demos and see all the excellent stuff being done by the NREN community and shared in sheer generosity. There's several good posters for the student poster competition. The students who've done them will be available to meet and talk to you in the afternoon coffee break. And then, of course, the most important announcement. There's a gala dinner tonight, and if you want to participate, there will be historic trams leaving from here to take you there. And you should join the trams because there will be drinks served on these historic trams. And it will be a good trip and a good way to experience Prague. The trams will leave from the lobby, downstairs, second floor. Guides will take you to the tram stop. 7:15, 7 o'clock, and 7:15. And these are trams. They travel on the tram tracks of Prague, so they can't be delayed. They can't wait for you. This is one way we have to abide with the rules of the outside world and the NREN community, even though we don't like it. So, welcome. Thank you very much.